Hello, my name is Pradibhati, and this is a lecture on Association mining for Data 630. In this lecture, we cover about some of the basics of Association mining, such as the logic and the principle behind extracting rules. How do we formally represent knowledge in Association mining? And we cover about some of the commonly used formal or quantitative metrics to evaluate individual rules extracted from transaction databases and frequent item sets. Um, those are the metrics used to measure the validity and relevance of individual illustration rules. And we cover a very commonly used simple association mining algorithm called a priori algorithm. And we go over an example application of association mining in R. In subsequent modules of this course, we will study two broad categories of machine learning algorithms, namely supervised learning and unsupervised learning. In supervised learning, you have a training sample where you have annotated targets or dependent variables. And from those observations, you apply some kind of logic or algorithm to fit a model or a function to estimate future classification of of the target variable in the context of classification, in the case of a regression application where your target variable is quantitative value, then that is for estimating or predicting the quantitative value of the target variable. That is a supervised learning paradigm. In unsupervised learning, you don't have a target, you don't have a labeled or annotated dependent variable. So the exercise in unsupervised learning is to logically create groupings of the observation or the instances in your data set. Typically, the common metric used for creating that grouping is some kind of similarity matrix. And clustering is a primary example of that kind of unsupervised learning. Here in association mining, which is also a type of unsupervised learning, the objective is to find objects or attributes or variables that happen together, okay, with relatively high frequency. Now, that frequency, what is considered frequent, is formally evaluated using a quantitative metric that we will discuss in this lecture. Support and confidence are the two main quantitative metrics to evaluate the frequency of items as well as the confidence of the rule extracted from those items. And then we'll cover those in subsequent slides. So what are some application of association mining? Now, we can apply association mining in different domains, in different contexts. But one domain that popularized the use of association mining, particularly is a priori algorithm, is a retail industry. So that's an application when, for instance, in a retail store, you go for shopping, you purchase different items, and that makes one transaction. And the items are collectively called your basket, right? That's a one transaction. In a retail store, collectively from different transactions, potentially can extract useful rules by identifying first frequent items, say things that are purchased frequently together, and then extracting useful rules to say maximize profit. And for instance, one strategy that you see in example application in a widely mentioned application is by putting different items that are purchased together in same area, same location, you are maximizing the purchase of those items. So that's one application and a very common application, at least in a priori algorithm application. A similar application is, for instance, search items. What are terms that are frequently used in certain searches? So potentially you can identify those terms that are used together for some areas of searches or some type of search. Okay. You can also apply association mining in other domains such as engineering applications, okay, or any safety domain. For instance, one area that I have used association mining is for extracting factors that lead to an undesirable event or accident in air traffic operation. So when a particular flight goes wrong, usually there are factors that contribute to the outcome of that event. So by applying association mining, you can potentially discover rules, useful rules, that by identifying factors that are responsible for that kind or a similar kind of event or undesirable outcome. Okay, how do we formally represent knowledge in association mining? Again, the goal or the objective in association mining is to leverage a relation between different items, okay, and use that to identify useful patterns called rules, okay? For example, if you have a database with items such as A, B, C, D, E, and F, typically what is involved in extracting useful rules is first you identify or discover the commonly occurring frequent item sets. Okay, in this example, for instance, if we determine A, C, D to be frequent item set, again, that is formally quantified through the use of a threshold value for the support metric, which we will cover in upcoming slides. Now you can potentially extract rules such as AD leading to an outcome in C from this item set. Okay, so the exercise in association mining is first you identify frequent item sets, and from those item sets you can potentially extract useful rules that satisfy some level of confidence. Okay, formally, one important thing that to note here in the difference between the model we have in association mining and other supervised learning. In other supervised learning context, you have a training set, you apply some kind of learning rule or algorithm, and you fit a model. So you have a single model that you can employ for future classification or regression application. Here you don't have a single model. What you have is a collection of rules that will collectively make your model. Okay? So you're extracting rules. It's not a prediction application. Okay, formally, this is how we capture the rules in if-then statements, right? So if items in set X happens, and if we have some level of confidence to satisfy the rule as being potentially useful, leading to an outcome in Y, that is in item set that in set Y, is a rule. The part that captures the if part of this statement is formally called an antecedent, and the items in Y are called consequent, or the then part of the rule. So next simple example is if you identify a rule to be useful or interesting, satisfying both the support and the confidence level, such as these. What this means when we're interpreting this rule is if a customer buys milk, you will have some level of confidence that that customer will also purchase bread. And so the same goes for diaper and beer. Again, you can apply this in any domain where you have objects or variables that can be combined together in some fashion. Okay. Evaluation metrics. Okay. So we talked about identifying frequent item set, from those item set extracting rules. But how do we formally qualify those item sets in confidence and the extracted rules? So one of the widely used or commonly used for a prior algorithm is support. Support is the percentage of total transactions in the data set. So you put some threshold value for the support, and things that are considered frequent are measured against that threshold value. Okay. So informally, this is how often the items appear together in proportion to all the transactions. So you scan the entire transaction and then identify those frequent item set based on a support threshold. Okay, so it is a probability value, it's a probability of the items occurring given that transaction in the transaction database. And the way you calculate that is formally support of an item set is you count the number of transactions containing those item sets, the items
that are being considered and divided by the total transaction in the database. Okay, typically because the application of association mining is in large databases where you probably have sparse data, right? So unless you put the support value low, you won't identify potentially interesting rules. So in application, typically you use a support by small value support. And if you think about it, most interesting rules don't happen at a frequent uh, uh, in a frequent fashion, because if they do, you will probably have a knowledge already. You don't need any sophisticated rules to know they're useful. Okay, interesting patterns are something that don't happen quite often, but when they do happen, they're usually interesting and they're not obvious. Okay, so support is usually set to a low value. And the corresponding metric that goes with support in a priori application is confidence. Again, the first step is you discover the frequent item sets using a support threshold. Once you discover the frequent item set, then you extract rules from the already identified frequent item set. Okay, so confidence is a percentage of the total number of transactions in the data set in relation to the rules, to the frequent item set, not to the transaction, because you don't, in the process of extracting rules, you don't scan the entire transaction. You go over each frequent item set and extract the rules, and the rules are determined useful or not based on a confidence value. So informally, that is how often the items in the consequent appear whenever the items in X or in the antecedent part of the transaction occur. Okay. Informally, this is how you calculate that the confidence of the rule is a conditional probability, which means a probability of items in the consequent given the items observed in the antecedent part. Or you can alternatively calculate that as a support of the rule over the support of the items in the antecedent. And unlike the support, the confidence usually set to a higher value, like 80%, 90%. Okay? Because you want to have a level of confidence in the rules that are extracted from the item sets, the frequent item sets. Okay. And a third metric that is widely used together with support and confidence in a priori algorithm is called lift. It is a type of metric that combines support and confidence. And this is another way of safeguarding from rules that are extracted by random noise or chance. Okay? So it compares the frequency of an observed pattern with how often you would see that just by pure chance. Okay, and it is formally calculated. The lift of the rule is the confidence of the rule over the support of the items in the consequent. So typically, you want a large values for lift because the closer you are, the lift is to a value of 1 is likely, it is higher likely that that rule was extracted by, just random noise or chance. So the higher the lift is, the higher the likelihood it's actually useful or a real rule. Okay. Also, sometimes you use leverage. I rarely use leverage, but there are some cases where you have both high support and high confidence with a corresponding low lift. And sometimes those rules could be interesting. So you look at the leverage of the rules to further investigate them. And the way you calculate leverage is the leverage of the rule is the support, the difference between the support of the rule and the product of the consequent support, the antecedent and the support of the consequent. Okay. So how do you go about extracting the rules? The strategy in general involves two steps. The first one is you find all the items that occur more often. That means those items that satisfy the support threshold. And then once you do that, you go to the next step of extracting the rules. So during the second step, That means during rule extraction, you don't have to visit the entire transaction in the database. You just go over the items that were identified as frequent based on the support threshold. And then you test each rule, each potential rule against its confidence threshold, and keep those as interesting or potentially useful rules. And in subsequent slide, we go over these two steps. So for identifying all the item sets, frequent item set that is, you have to travel through all possible combinations in the transaction database. And that is computationally very expensive. It is exponential in the number of items. So for k items, for instance, you have 2 to the k minus 1 items. For instance, if you have 10 items in a transaction database, possibly you have to visit 1023 different possible combination of item sets, right? As you go to 20, for instance, you get to 1,000,000. So you can see how quickly the search space grows exponentially. So there is this property called anti-monotone property, which was pioneered by a priori algorithm, is such that if an item set is infrequent, if you determine that a given item set not satisfying the support threshold, then all of its supersets are also infrequent. That is, if you have, for instance, in your transactional database, A, B, C, D, E as items, and if you determine that A, B not satisfying the support threshold, in other words, if it is infrequent, then all item sets containing A, B, that means all its superset will also be infrequent. Okay, and you leverage this property to cut or to trim the exponential search space. And this property is called anti-monotone property. And applying this strategy for cutting the search space is called support-based pruning. Okay, visually, maybe it's easier to understand. Let's say if you have 5 items, A, B, C, D, in your transaction database. So in a bottom-up search, you start with an empty set, and then you go to the next items. That means containing all items containing one element, A, B, C, D, and E individually, right? In this case, all satisfying the threshold value, the support threshold value. And then you move on to the next level of item set, and in here, A, B, 2 item sets, A, B, A, C, and so forth. So if you determine that A, B does not satisfy the threshold value or found to be infrequent, then all of its subsets, that is every set that containing A, B, will also be infrequent. So there is no reason for you to search that space. You can completely ignore it and cut the search space by applying this property. So applying this property, you can significantly reduce the search space, and this is called anti-monotone property. So this is the first strategy. That means you apply this during searching the items, the frequent item sets. So the next step is, once you search, you identify all the frequent item sets in the transaction, then you extract rules from those item sets. Okay, that means for each frequent item set, you extract all possible rules that satisfy the confidence threshold. So you'll have threshold for the confidence, and then you have the separate threshold for the support, as we discussed in the previous slides. So the way you do it is by partitioning the item set into 2 non-empty subsets. So remember, each rule will have 2 components: it's the if part and the then part. Okay, so that means each possible item set, each frequent item set will have to be split into 2. Okay. And computing the confidence does not require additional scan. This is another important item, is because you are working against the items that are frequent. There is no reason to traverse through the entire transaction in the database, because you already, by the second step, you have already identified all the frequent item set. Okay. So in general, there is 2 to the k minus 2 possible way of splitting a given item set. Okay. So for instance, if ABC is your frequent item set, 2 to the third minus 2, 6 potential candidate rules, right? So that means if you don't apply any optimization, search optimization, you have to visit all this space and test against the confidence threshold. That means A to BC, B to AC, C to AB. So every possible split into two components you have to visit. And the way you calculate the confidence for each rule is by dividing the support of the frequent item set over the support of the antecedent. Okay. In general, if the item set already, I mean, you going over the item set that are frequent. So if the item set is frequent, any subset of it is frequent, right? So that properly holds. Okay. Then initially, so the strategy that's applied in here, the way the rules are extracted is first you identify all the rules that have only one element in the consequent part. And then subsequent items, like subsequent rules are extracted from that rule. Okay, that is how this strategy applies. Now, the anti-monotone property that we leverage for identifying frequent items set to cut the number of searches of the search space does not in general apply for the confidence part, the rule generation part, but it applies partially to individual rules, individual item sets rather. So that means if x leading to the difference of y on x, splitting into 2, does not satisfy the confidence threshold, then a subset of the antecedent part leading to a corresponding consequent also does not satisfy. It's easier to explain that in an example. For instance, if ACD leading to B does not meet the confidence threshold, okay, one of the rules that you extracted from ACDB item set, which is this one, ACD on the antecedent part and B on the consequent part, if you find that not satisfying the confidence threshold, then all the rules that contain a subset of the antecedent will also not satisfy the confidence threshold. So anything containing this, a subset AC, BD, AC to corresponding BD, AD to BC, and so on and so forth. All those that are a subset of the antecedent will not satisfy. So you are also applying partially the anti-monotone property on individual subset. Again, it's easier to explain than visual graphs here. So ABCD is the items that they are considering to extract rules from. So if you happen to find BCD leading to A, for instance, here not satisfying the confidence threshold, that is, if it is a low confidence rule, that means any rules that are extracted from this set with a subset on the antecedent side, like CD. CD is a subset of BCD. BD is a subset of CD. All of those leading to resulting in corresponding consequent items will also be low confidence rule. So that means you can cut the space, the search space, applying this logic or this strategy on each individual items. Okay. So this is an example of doing association mining in R. By the way, I will not provide details about some of the function in the rules package and the rules-based package. For each module, we have tutorials provided by the TA. So the details of the programming aspect of each module or each topic that we cover in each module will be covered in the practice exercise and by the tutorial videos. So this is primarily an overview of how you do association mining in R, and for this particular data set, which is the books data. Okay. So first thing, in any data science effort or in any data mining project is understanding the objective, understanding the problem domain. Okay. So you have to have the data, understand the nature of the data. In this case, we are trying to understand the book's purchasing patterns of customers. So our customers are on transactions, and based on their purchasing pattern or rating pattern, we want to identify those customers, potentially to do some kind of promotion to those customers based on their interest. Okay, this is just one application. So the transaction will be the customers, and the books that they rate or purchase will be the items. Okay. Two rules package for the relevant packages for a rules pack, rather a priori algorithms or a rules package and a rules vis package. One is for actually extracting the rules. The rules vis package is for visualization. Sometimes you need to visualize to have a better understanding of the rules generated. Okay, here is the few cases of the data. As you can see here, a few instances of the data. The user ID, they're rating for any given book. This is the title of the book. For the purpose of extracting rules, in this particular example, we're not going to be using the rating. Okay, again, not unique to association mining. In any project, data mining project, most likely you'll have to do some kind of data preparation. It's unlikely will you find that data will be clean. In most real application, you would have to clean the data. So for instance, in this application, you have to remove any unique fields if you have some, and also because a priori algorithm cannot handle quantitative values, you have to do some kind of discretization. As we cover some of the discretization technique that we covered in module 1, you can apply for this case. Okay, so first thing, you load the data. Here I'm using the read transaction function, which is a way to, if the data doesn't come in transaction format, you can use this function. If already it's in transaction format, the data has been already formatted, then you can just use one of the functions, a simple reading function like the read CSV file function. So we reading the data here, and we loading in a single format of a single. What that means is each items will be on its own row, individual row. So another option is to load it in a basket, so that individual row will have all the items saved in a basket. So this is a tab separated file, so the separation will be tab, and we're interested to load only the user ID and the title of the book. And we're removing duplicates here just in case that some customers purchased, different version of the same book, so you don't consider that multiple different books. Okay, here is the summary of the loaded data. As you can see, there are 92,108 transactions. Those are the rows, the customers, and there are 220,447 items, books. Okay, here are a few cases of the book titles, like 5 cases, and the corresponding customer IDs. Okay, so here I apply the size function, which is part of the rules package, to calculate the size of the basket. And here is the summary. As you can see, more than 50% of the cases have only customers have only purchased one item. So the basket size is just one. Basket size is for each customer the number of books they have purchased. Okay, there's some outliers, as you can see, in some cases where 10,850 items. Another function is item frequency, which counts the books, and I'm here normalizing by the number of the basket size here, and I'm sorting it. So this is just a basic kind of exploring the data. So I listed the books and I sorted them according to the number of frequency, their frequency. And as you can see, the highest frequent items is this book right here. Is called Wild Animus, and it happened 2,502 times. Okay, so In the previous slide, we have seen that the transaction has a total of more than 90,000 transactions. And here, even the most frequent item is only 2,500, which is, if you just normalize it by the number of transactions, less than 3%. Okay, that tells you the level of the sparsity in the database, and you want to leverage that information, before you feed the function, which is part of the data preparation that you have to do. So this is just the same information visualized. Again, a large number of cases are small counts. Most are aggregated in this area. So as you go further in the number of counts, the number of cases are very small. Okay. Again, the same information displayed in visualization. And here, as you can see, 50% of the cases right here are less than 1. By definition, when you are doing association mining, it's a pattern identification process, right? If a customer purchases only one book, there is no real pattern that you can learn from this customer. So you can safely remove the number of cases and do some optimization, pre-optimization for the search space. Now, in early discussion that I mentioned, there are some optimization in the search strategy through pruning, like support-based pruning. But the reality is, a priori algorithm still makes multiple trips or multiple scans of the transaction database. So to the extent you can, cutting the number of transactions that are not relevant for the rules is going to optimize the search further. So that means here I removed all the cases where the number of transactions or the number of items is less than 1. I'm keeping only greater than 1. That cut into but more than 50%. It was a 90 more than 90,000 transaction now. Potentially, I'm looking rules only through the 40,000 and 122 cases or transactions. So these are the kind of preparation. It depends on the data that you will be working with, but you have to always look at the data first, and to the extent you can clean the data or optimize it so that further analysis can be handled in an efficient manner. Okay, here are the priori rules. So this part of the errors package, this is the main function that feeds that extract rules. So I am passing to this function the transaction database, data set, and I'm passing two parameters. These are the core parameters that we discussed earlier, the support and the confidence. Here I'm saying, again, we discussed this, typically you put a low value for the support. Here I'm using 0.2%, and for the confidence, 75%. Okay. Now that returns the rule, so it goes through the transaction and apply the logic that we discussed earlier and extracted the rules that satisfy this condition. So it returns 191 rules here, and this is a distribution, and it shows here that the length of each category of the rules. So rule length is basically the count of items both in the left-hand side of the rule and the right-hand side of the rule. So the sum of the items in each rule. So here with the distribution, 11 of the rules have only 2 items. That means 1 on the left and 1 on the right. And 100 of the cases have 3 items. 66 of the rules 4 items, and 14 of the rules have 5. By default, a priori algorithms in R limits to 5 lengths of 5, rule lengths of 5, which you can change, but right now that's part of the reason why you don't see more than 5. It was limited to 5. So here is most rules contain 3 items, as you can see. There are 100 rules with rule lengths of 3. And here is summary. This summary of the support, the confidence, and the lift on aggregate for all the 192 rules. Okay, support, the means the first quartile, the median, the mean in the third quartile for the 191 rules. So this is an aggregate level. Okay, this is just summary of the rules. And here I'm using another function to inspect the rules generated. Okay, so I am picking the head, which is 5 rules. I'm picking 5 rules sorted by confidence, and I'm inspecting them. And they're displayed right here. So for instance, right here, the antecedent or the left side of the rule is, these are the books. These are the items in the transaction. So 4 to score, high 5, 7 up, 2 for the doll. So these 4 items on the antecedent side are leading to the 3 to get deadly on the consequence side. So that means customer who purchased these books also purchased these books, and that starts with a 98.8 confidence. And the number of cases that satisfy these conditions are 0.2%, which is the support. And the lift, as we discussed earlier, which combines support and confidence, is a high number, rather high number. So this is more or less a real rule, which was not generated through random noise. As you go, we're displaying 5 rules. The next one is the Harry Potter series books, and just from looking at it, it just kind of makes sense that people who buy books in series tend to purchase the next sequel. So, Harry Potter books, all these customer who purchase this also buy this book, which is the next sequel, and then again the corresponding support level and confidence in the lift value are displayed here. Again, this is some kind of inspection you can do once you extract rule. It is in general it's iterative process. It's not one time to make you go back, because based on some domain knowledge, the rules that are extracted sometimes are obvious and you don't want to use them. They're not interesting enough because there's existing knowledge about them. So it's an iterative process. You inspect rules, you modify some of the parameters that you pass for rule extraction function, and so forth. Okay, I only used 2 options earlier when I called the function a priority function, right? But there are many other options that you can pass to the function called. One of them is appearance. Appearance is the way you control the number of items in the left-hand side and the right-hand side. Okay, I haven't used it, but it's a commonly used option in that function. Another one is an interest measure. Again, we only covered lift, support, and confidence when we discussed about the formal measures, quantity metric to evaluate different rules. But there are others, depending on the data set, depending on the application, you might want to consider to look at other metrics to evaluate rules. Another important element of rule extraction is removing redundant rules. Redundant rules are rules that are a specific version of a given rule that do not provide any additional knowledge. So an example is if you have an item A resulting in an item C on the consequence side, and if there is a specific form of that rule that contains A and B and the antecedent section resulting in the same C with the same level of confidence, that rule is a specific version of the more general rule. So you're not learning anything more unless the confidence is higher in the specific case. So in fact, there is a function or an option in R to show you the benefit or the additional information gain of that specific rule. If there is no additional benefit or information gained, then you can safely ignore that. There are 2 ways removing this. I think the latest version of our errors package in R has a built-in function to remove redundant rules. And another way of doing that is using matrix manipulation, using like diagonal matrix, which is covered in the tutorial practice, and most likely the TS will go over this as well. Okay, but it's important to know about redundant rules. Visualization as a critical component. Sometimes visualization helps a lot to identify group if there is any grouping, any patterns, or any correlation that can be seen visually. So the AirRules Viz package provides some function, and it can generate different kind of graphs or visualizations: scatter plot, parallel coordinate, grouped, mosaic, and the matrix. So again, the practice tutorial will go over how to generate and interpret these plots. Other algorithm for association mining. In this lecture, I went over only a priori algorithm, but this is not the only algorithm, although it is the simplest and the commonly used one. The optimization, the search optimization we discussed, such as the support-based pruning, even with that, the a priori algorithm does multiple scan of the transaction database. So when you have large databases, it's likely that the performance of a priori algorithm is not optimal. So sometimes you might want to consider other association mining algorithms, such as equivalent class transformation, frequent pattern, dynamic programming. I haven't used any of these for production use, beyond reading and experimenting with them for just my own understanding. But just good to know that they exist. There are different application or a different way of doing association mining. As far as the resources go, there are a lot on the web, as you know, and we provided quite a bit of resources in the class in the module page. And there are also numerous tutorials on YouTube that you can find that go on provide details about how you would do association mining, a priori, and others. But I think the ones we covered here provide the basics and the foundation of a priori algorithm. You may have some questions which we will address in class, and thanks for listening.